A little countdown. All right, chapter 2, chemistry. And everyone's like, I already took chemistry. Do you have to take chemistry before you take A&P? Or sometimes I don't know if you could take it together. You're like, oh, I thought I'd never have to do it again. Unfortunately, when we go all the way down to the cellular level, we have to talk about ions. We have to talk about things moving. We have to talk about bonds. That's all the chemistry portion of it. So we have to do a little refresher. So it's my chapter 2. Hopefully it won't bore you too much. The basics of my chapter 2, the chemistry parts, are some terms. The first one is matter. Matter is anything that has mass. It's got mass. See it, hold it. And it occupies space. Not to be confused with weight, because a lot of times they're used interchangeably. Weight is just talking about the pull of gravity on mass. So your weight can change. If I headed to the moon, my weight would be less. That doesn't mean I lost any weight. And I'm like, it's just that gravity changed. And I'm like, but mass does not change. Now there are 3 states of matter: solids, liquids, and gas. Solid is a definite shape and volume. I can see it. I can measure it somehow. A liquid, it has a changeable shape, but it has a definite volume. I can take a liquid and I can pour it into any cup I want, and it will form into that same shape of whatever container I put it into. But it's still the same amount of volume. If I take 100 milliliters of liquid and I pour it into one cup, and then I pour it into a different size cup, it's still 100 milliliters, but it changes shape. Gas can change both. It can change whatever shape it's in, and it can change its volume, based usually on temperature and pressure. So it can change volume. It can get bigger. It can get less. It can, it can change both of those. Now, that's as much as we get on matter stuff. Energy, we talk more about. Energy is the capacity to do work or put this matter into motion. And there are 2 types. There's potential and there's kinetic. Kinetic is energy in action. We can see something moving. Like we can actually see something changing, something doing something. Potential, it's just stored energy. It's not doing anything yet, but it has the potential to do something. Now, energy can be transferred from potential to kinetic energy. We'll get there in a second of how this can happen very commonly every day. So we can go with stored energy and change it into kinetic energy. Storing energy, and then we can make it do work with kinetic energy. Now, my example with that, and I'm like, is we have chemical energy. It's a type. Well, before I would say it, we'll see if you can guess. It's energy stored in bonds. So chemical energy is energy stored in bonds. We talk a lot about chemical energy in this class. Not just in this lecture, but later on when we talk about breaking bonds. Chemical energy is energy stored in bonds. When I smush 2 things together and make them stay there, there is energy in that bond that holds them together. The biggest common example with this is ATP. And I'm like, who knows what ATP stands for? Yeah, triphosphate. So how many phosphates are there? 3. And when we shove those 3 together, there is energy between each of those. By holding those 3 phosphates together, there's energy between those phosphates. I can break one off and I can release energy. Now, because it is a type of energy stored in bonds, what type of energy is that? Kinetic or potential? Potential, because it's stored. It is a stored energy. It's just hanging out there. It's not doing anything yet, but it's there, just ready to do something. Now, things it could do. Other types of energy. Electrical energy. If I'm talking about electrical energy, I'm talking about moving of charged particles. And we'll talk about charged particles coming up. But it's charged particles, things that have positive and negative charges, and moving of these. Now, because particles are moving, kinetic or potential? Kinetic, it's energy in motion. I'm like, things are moving. So we can use chemical energy, break that bond, release energy, and then make particles move. Mechanical energy is moving matter. I am not just moving charged things that you can't even see. And I'm like, I am physically moving something. Example, I can move my muscle. We can all see this. I'm moving matter right now. And I'm like, I am moving my muscles. I got a lot of things going on to make that all happen. But I'm like, but I'm moving matter. I'm moving muscles. I'm moving bones. That's all part of me. That's all part of matter. Kinetic or potential? Kinetic, energy and motion. The last type of energy is radiant or electromagnetic energy. We do not talk about this a whole lot in this class. We briefly mention it in some units. This is any type of energy that travels in waves. Visible light travels in waves. Ultraviolet light travels in waves. And X-rays travel in waves. And I'm like, so it's energy that travels in waves. Any guess what type of energy? It's kinetic. It's energy in motion. Now, as I've already been kind of mentioning, yes, energy can be converted from one form to the other. It can easily go from chemical energy to another type of energy. Now, it's not always the most efficient. When we are changing one energy source to another, it is not very efficient. Our bodies are not 100%. And I'm like, and unfortunately, a lot of that energy, when we go from one source to another, it gets lost as heat. Which isn't always a bad thing, because it does help us maintain our 98.6 degree Fahrenheit temperature, but we lose energy. Common example of going from one energy to another. And I'm like, if I go back, chemical energy is energy stored in bonds. Now, if I go to the grocery store and I'm checking out, what do they always have for sale near the checkout of the grocery store? Candy. It's always the candy bars. Now, if I look at a Snickers bar, what type of energy is in that Snickers bar? I'm looking at it on the shelf. There is sugar, which is what type of energy? Potential. Which is, yep. And so which is our one potential? It is a chemical. There's chemical energy in that Snickers bar. Because there's all these bonds that form all of the molecules of all the sugar, and there's protein in there. You can almost say it's healthy. But there's stored energy in that Snickers bar. But when I look at it, debating if I want to buy it or not, is it giving me any energy to do anything? Nope. But if I eat it, then what? Then I have energy, and I can bounce around, I can do whatever. And so I'm like, I can take chemical energy, I can eat my Snickers bar, which has this potential, the stored energy and all those bonds. I eat it. What happens to all those bonds in my digestive system? I'm breaking them apart, and I'm like, and as I break all those bonds, I release energy, and then you have lots and lots of energy to go run and do whatever else you need to do. And I'm like, and I'm going from a potential type of energy to a kinetic energy. And if I'm using it to go run, I'm going to take that chemical energy that was in the Snickers bar, and I'm going to turn it into mechanical energy, and I'm going to move my body. Now, it's not efficient. If there's, I don't know, 200 calories in a Snickers bar, I don't know how many there are. And I'm like, it provides so much energy. That doesn't mean every single part of energy, when I break every single one of the bonds in there, that does not mean all of that energy released moves me forward. Like, if I remember correctly, it's about 40%-ish. And I'm like, 40% of the energy in the Snickers bar actually moves me. Most of the rest of it is lost as heat. We are not the most efficient. It's unfortunately the same thing that happens in your car. And I'm like, gasoline has lots of stored energy. It has lots of chemical energy. Our engines break all the bonds in that gasoline, and it allows our car to move forward. Kinetic energy or mechanical energy. Not efficient, because what happens to your car engine after it runs for a while? Well, yes. And I'm like, but it will produce heat, which in the winter months it's great, because that's how our heater runs. Otherwise, we don't have anything else that's making heat. It's all that extra energy lost as heat. I think I read a thing somewhere. It's around like 30 to 40% of the energy in your gasoline actually moves you from point A to point B. All the rest is just lost as heat. Sounds like a waste of money. Now, some other things dealing with matter are elements. Elements are found, say, matter is composed of elements. Elements make up matter. Now, an element is the simplest part that can make up matter. They can't be broken down by any type of chemical, normal thing. There are some labs that can try to do weird things to things, but they are not broken down. And every element that we can find on the periodic table has its own unique properties. Some are physical properties, some are chemical properties on how it behaves. Now, physical properties mean something that we can detect with our senses. Gold is an element. By looking at gold, what color is it? Yeah, it's kind of like it's a goldish color. And I'm like, it's got to be yellowish color. That's a physical property. All gold is going to be the same color. And I'm like, so that's just something we can see. Now, chemical properties is how it behaves with other elements. Does it like to be reactive? Does it like to be off by itself? And we'll talk about some examples of things that are reactive. Now, atoms are in elements. We don't break elements down, but atoms are in elements. And the atoms that are in the element give that element all of its unique physical and chemical characteristics. Now, when you look at the periodic table, you've all seen a periodic table at some point in your life. Elements are always given some type of atomic symbol on the periodic table. It's usually a 1 or 2 letter abbreviation for that element. Sometimes it's the first letter, sometimes it's the first 2 letters, sometimes it's some other random letter that usually comes from some background information. But that's the atomic symbol. It's that 1 or 2 letter and a shorthand for the element. What's C stand for? Carbon. In our body, there are 4 elements. They make up about 96% of you. So 96-ish% of you is made up of carbon, hydrogen, oxygen, and nitrogen. Now if you're like, how am I going to remember those 4? They spelled Tron. It's not a real word, but we can pretend. And you're like, well, what makes up the other 3.9% of me? There we go. The other 3.9% of you is primarily phosphorus and sulfur. Those are kind of those top 2, of the next 9. There's calcium, potassium, sodium, chlorine, magnesium, iodine, and iron. Now, some people will ask, what are the top 4 elements that make up you? Some want to know the top 6. So I kind of bolded phosphorus and sulfur. So some people, if you want to, I'm going to mix these around a little bit. If you include all of them, you can pretend that this is another word called trinops. No, not a real word. But there's all your top 6 elements. It's not a real word. We're just pretending. Now, our atoms, which make up elements, have even smaller things that make up them. So we call them subatomic particles. And there's 3 of them: protons, neutrons, and electrons. Now, protons and neutrons are found in the nucleus of an atom. An electron is the one that's kind of like kicked out and hangs out by itself, and what they call the electron cloud outside of the nucleus. I'll draw some of these in a little bit. Now, the nucleus, here's my nucleus. The nucleus, and what 2 things are in there? Oh, it's up there. Neutrons and protons. Neutrons and protons both have mass. And so almost the entire mass of whatever atom it is I draw is all found in the nucleus, from the mass of the neutrons and the protons. Now neutrons, as their name implies, is neutral. It has no charge. Its mass is considered 1 atomic mass unit. It's like its own little unit. Protons carry a positive charge. What was that? Oh, I was going to say protons carry a positive charge. They both start with the letter P, protons for positive. And it also has the exact same mass what a neutron has, 1 atomic mass unit. Electrons, these things that hang out in the electron cloud out here. They carry a negative charge. So we have positive, negative, and neutral. I usually try to remember, or tell people to remember, neutron for neutral, no charge. Protons for positive, they both start with a P, and then you just have to remember electrons, that weird one that is negative. Now, it has almost no mass. It has 1/2000th the mass of a proton. So we just round that down and say it has no mass. Now, on an element, a stable element on our periodic table, the number of protons equals the number of electrons. So if I have an element that has 8 protons, how many electrons does it have? 8. Protons and electrons in a nice stable element are going to be the same. Draw some in a little bit. Periodic table. I'm going to draw some stuff in a minute. What's Na stand for? Sodium. If you're like, why doesn't it just start with SO? It comes, I think, from Greek for natrium, which means the rock. It's like a rock salt. Random factoid. But the atomic number is written always on the periodic table. It will tell you this is your atomic number. It is the number of protons that are in the nucleus. So sodium has 11 protons in its nucleus. How many electrons does it have? It has 11. Number should be the same. The other number that we find on a periodic table is the mass number or atomic mass. I've heard it called both things. The word mass is in it. I'll put atomic mass or mass number. It's the number of protons and neutrons. It's talking about what all together is in that nucleus. So a total number. And according to this, sodium has an atomic mass of 23. And we know it has 11 protons, because that's what that told us. How many neutrons does it have? It's like math today. 12. Hopefully that wasn't too hard a math. So I know the number of protons. That told me that. And then I have to do the math. They're usually pretty close to the same number, and sometimes they even are. But it will tell you the number of neutrons that are in there. Then we get the weird oddities. There's our basic elements on our periodic table. Then we have isotopes. These are variations of atoms. It's because the neutrons can change. The number of neutrons can change. Neutrons can change. Can protons change? No, or it would be a completely different element, which we can't do that. And I'm like, but the number of neutrons can change. And there are some elements that we find these isotopes more common in nature, where they have varying numbers of neutrons. So the atomic number is always the same. The example they give on this one is that carbon. Carbon has an atomic number of 6, and it has an atomic mass of like 12.001, something like that. There's a reason for that 0.001 or 0.01. What does the 6 tell you? It's our number of protons. So if I had to draw it, I have 6 protons in the nucleus. How many neutrons do I have? Round it. 6, because the 2 together equal 12. How many electrons do I have? I have 6. Now, what can happen with carbon, and it does, and like this number of neutrons can change in nature. There are some carbon atoms that are out there that have 7 neutrons. Some have 8 neutrons. They're very unstable. I'm like, but they can change their number of neutrons. And so sometimes we call this carbon-12. Our basic carbon, carbon-12. That's what most carbon out there is. But if it starts to have extra neutrons, we'll call it carbon-13 or carbon-14. Now, do you think it likes to have these extra neutrons? But way extra? Would you like to have extra things weighing you down? Nope. And so it tries to lose these neutrons. It tries to get rid of them, which makes it unstable. And so carbon-14 tries to lose the neutrons, those extra neutrons, and eventually it will break down to carbon-12. Now, that's the basics of carbon dating. And like when we try to figure out how old things are, we know how long it takes for carbon-14 to break down to carbon-12. Now, the atomic weight, I was going to say, is the more accurate atomic mass. There's a reason we always round these for our benefits, but there's a reason why it's the 12.001 or 12.01 on there. Is we look out in the environment, how many carbon-12s are there out there in the world? How many carbon-13s are there? How many carbon-14s, approximately? And I'm like, and we make an average of all of them. So since we know there are some carbons out there that have extra neutrons, it's never just a straight 12. Because we know there's a few out there that have extra neutrons, which means mass is just a little bit higher. It's an average. So if you ever wonder why it's not just a straight number, it's because you know that there's some heavy isotopes out there in nature. For our benefit, we just round to the nearest whole number. Now, why do we care about these heavy isotopes? Since they like to lose their neutrons, which makes them unstable, we can use them. Now, as they start to break down and they lose their neutrons, we call them radioactive. And you're like, well, that's never good. But we can use them to our benefit in the medical field. One, we can detect this breakdown of neutrons in our body. They can give you, like, have you ever heard, maybe you guys have had it, like radioactive barium? And I'm like, or if you've known someone that's had to drink the radioactive barium, from what I hear it tastes like chalk, and you have to drink a whole bunch of it. I'm like, now, yes, they are drinking a heavy barium mixture. And you're like, oh my God, they're drinking radioactive stuff. It breaks down very, very quickly, so it's not going to create a lot of problems in the body. But when you drink this radioactive fluid, it can travel to different parts of the body depending on what parts of the body like to uptake the barium. And yes, under a scanner, you glow. And certain parts of our body, we can see glowing with radioactivity, which makes things stand out really well, and we can get really clear images. Now, we can also do this with iodine. Radioactive iodine is used twofold. Radioactive iodine, does anyone know what part of the body breaks it down? The thyroid. And I'm like, so people that have thyroid problems, the iodine goes straight to the thyroid to get broken down. Now, because we know that, and we can give someone radioactive iodine, yes, it will glow on an image. But we can also give someone continuous amounts of radioactive iodine, and you're like, that doesn't sound good. The only time they would do that is if there are thyroid problems, or you have hyperthyroidism, something that we need to actually kill some of the thyroid gland. If you have cancer around your thyroid gland, they may give you radioactive iodine, knowing that that iodine will go straight to that part of the body, not affect anything else, and it will start to damage or break down some of the cancer cells or just break down some of the thyroid so it's not so hyperactive anymore. So we can use some of this to our benefit. Now, that doesn't mean it's all good. Yes, if you're exposed to a lot of this, on a day-to-day basis, it can cause problems because it is unstable. But we figured out some ways that we can use it too. Oh, here's some of my examples. I was going to say, some of this I had. Yes, they are similar to their stable isotopes. So iodine is similar to radioactive iodine. Your thyroid gland doesn't care. We use it for diagnosing various things. Some are used to destroy cancers. Problems can become with radon and uranium. If either of those break down, they can cause cancers. Now, where do you find radon? What part of your house? In the basement. Yep, inside in the basement. They're always detecting for that. Doesn't mean every house has it. But radon is found in the ground, and if you have cracks in your foundation, that gas given off can end up in your basement. Never usually a problem unless you've got a your bedroom's in the basement and you have cracks and it's giving off a lot of radon. It puts you at an increased risk. You can get detected for it. But it's bad if you're exposed to this long term. Some other terms with chemistry, when we are combining things, when we're combining these elements, because we don't want to talk just about carbon and just about sodium. If we're combining things, when you have two molecules of the same atom combined together, we call it a molecule. So a hydrogen stuck to a hydrogen, they're both the same thing. An oxygen stuck to an oxygen, both the same thing. We call them molecules. When you have two different kinds of atoms bonded, we call it a compound. It's different, it's more compound. So C6H12O6, what is that? Anya, what does that stand? It is, but if you put these all together, it's a type of sugar. I heard someone. Glucose, because you're going to see this come up a lot this semester, and I'm like, it's glucose, but there's three different, not just two, but there are even three different compounds that we smush all together to make some type of, or three different atoms we smush together to make some kind of compound. Now, I don't know if you can read the little picture that I had up here. It says, caution, no fishing. Water area contains large amounts of dihydrogen monoxide. Any guess what that is? First, would you be scared if you saw that? You're like, oh, that sounds horrible. Anyone guess what dihydrogen monoxide is? Fancy. Sounds scary. But no, it's just water. And I'm like, so, water. Is water a molecule or a compound? It's a compound because it has both hydrogen and it has oxygen. Two different atoms smushed together. It's considered a compound. Now, when I say smushing together, they like to smush together. I'm talking about bonds. Again, things we can break and release energy. But a chemical bond, these are relationships, energy relationships between electrons of reacting atoms. So I care about the number of electrons. I want to know how many electrons things have. Now, if I look at a periodic table and I have sodium up there, how many electrons does sodium have? It has 11. It's always the same number as protons on a periodic table. But it can lose one or it can gain one, but it starts off as, it has 11. Now, electrons, again, they hang out in this electron cloud, and they hang out in shells. So they hang out, aka in circles. That's the easiest way to say it. They hang out in circles. Now, when I'm talking about the electrons hanging out in the circles, I only care about the ones in the far outer circle. I could care less about the ones on the inside. The ones on the outside are the ones that are going to do something. The ones on the inside are like safe and protected. The ones on the outside can do something. Now, we call this the octet rule. I'm like, I know I'm going to draw some of this over again, but it might look nicer. Get out of the way. Here's my sodium. I know I said already. How many protons? 11. How many neutrons? 12. How many electrons? 11. I have to draw 11 electrons. I'm going to make them all little tiny dots. Now, the first, because they like to hang out in these circles, or shells as they call it, the first is happy and full with 2. Everything else after that is 8. That's why it's called the octet rule. Other than that first one that holds 2, everything else is 8. So, here are 2 electrons, my little black circles. How many more do I still have to draw? I have 11 protons, 11 electrons. So here's 8. They like to hang out in pairs, not always. So that one has 8 in it. Is it full with 8? Yes. But how many do I still have left? 1. There's my next one. Big one. I'll just so you can see it. Now, do you think it's happy all by itself? No, it wants to be 8. It doesn't like being all by itself. The shell is full at 8 and it's happy when it has 8. Now, I know I'm going to jump ahead. That's okay. Chloride. On the periodic table, it has an atomic number of 17. I shouldn't have drawn my circle so big. Smaller nucleus. How many protons are in there? 17. How many neutrons are in there? The atomic mass is 35. Again, I'm rounding it. So how many neutrons? 18. Because 17 plus 18 equals 35. How many electrons? 17. I have to draw 17 electrons, or aka 17 dots. There's 2. There's another 2. How many more do I have to go? 7? Should have drawn smaller. There's 2. Now, is it full with 7? Nope. So is it happy? Nope. It's going to want to do something. See, this is where I'm getting ahead of myself. We'll get there in a second. On how is it going to make itself happy? I'm going to come back to that in just a minute. I was going to say, they're all nice. They don't steal, they give, they share. Now, if we have an element on the periodic table that has all 8 in its outer shell, is it happy? Yeah. It's like, I'm happy. I don't want to have any type of reference. I don't care about anyone else. I am happy all here by myself in my happy little 8 electrons in the outer shell. That happens in all of the elements over on the right-hand side of the periodic table. All of these have 8 electrons in their outer shell. They are all those happy little things hanging out by themselves. They're called noble gases. They are unreactive because all their electrons are happy. They could care less. They're like, we have 8. We don't want any more. We don't want to give anyone. We are happy. The ones that don't have a full outer shell. Now, only because I'm like, what is a valence shell? The outer shell is sometimes called the valence shell. Just another word. So when your outer, aka valence shell, is not full, that's when it wants to do something, because neither of these elements are happy the way they are. So they're going to try to gain an electron, lose an electron, or share an electron to make them happy and stable. We'll get there. There's a reason I drew sodium. See, here's my sodium. 1 electron in its outer shell. There's some other examples. And there are 3 types of bonds that can happen when it starts to give or take or share electrons. The first type of bond that happens is known as an ionic bond. Now, in an ionic bond, we've got covalent hydrogen. In an ionic bond, an atom gains or loses an electron so that everything becomes stable and they'll become happy. But one thing has to give an electron, if it loses it. One thing gains an electron, and we call that an ionic bond. Now, when you gain an electron, what charge does an electron have? I think I've heard it. What is it? Negative. So if you gain an electron, what charge do you now have? Do you gain something negative? But you're negative. And I'm like, so if you gain something negative, you now have a negative charge. Now, if you lose, if you're the thing that gave away an electron, you lost something negative, what charge do you have? Positive. I always like to relate this. If you've got a bunch of people that you hang out with, we'll call them your friends. If you've got a bunch of friends that are negative people, and you like tell them, like, I don't want to hang out with anymore. If you get rid of the negative friends, you become more positive. Same basic idea. And I'm like, if something gives an away electron, it becomes positive. If it gains electrons, it becomes negative. Not that either of those are bad things. Now, they're going to transfer those electrons from their outer shell. So the valence shell electrons, their outer shell electrons, from one thing to another. So sodium and chloride are one of the most popular ones that we talk about because this has one electron in its outer shell. Now, it has a choice. It can either gain 7 electrons or lose 1. What's easier? Lose 1. If you're chlorine and you have 7 in your outer shell, is it easier to gain 1 or lose 7? Gain 1. You see how they like each other? Sodium's like, hey, I have 1 to give. And chlorine's like, hey, I could use 1. That one outer electron goes over to chlorine. Now, sodium lost an electron because it gave it. It was very nice. It was like, here, let me give it to you. I mean, it benefited too. It was happy now. But it gave an electron away. What happened to its charge then? It lost an electron. It becomes positive. And a lot of times you'll see sodium written as Na+, because it's always trying to give away that electron. Chlorine gained the electron. What charge does it have? Negative. And again, a lot of times you'll see chlorine with that negative symbol because it's always trying to pick up an extra electron. Now, we like to call the things that gain an electron and lose an electron, we have to give them names. So one of these, sodium or chlorine, becomes an anion, means it now has a negative charge because it gained an electron. Which one, sodium or chlorine, which one became the anion? The chlorine. It gained the electron, it's now negative. So which one is the cation, meaning it lost the electron and it became positive? Sodium. Now, you're going to see the words anion and cation from now on, like, for the rest of the semester. And you're like, how am I going to remember which one is positive and which one is negative? If you like cats, positive! Yay! Cats are positive! I like cats. My husband doesn't. You prefer just to, drive over one, which makes him happy, so yay! He doesn't go around killing cats. But, I'm like, cats are positive things. So cats are positive, and then you just have to remember anion's the negative one. Now, because these two things like each other, because they make a nice, I'll give you one, I'll take one, this giving of an electron creates what's known as an ionic bond. They try to hang out together as much as possible. Like, I'll give you, I'll take. Oh, you're so nice. Oh, let's hang out. That's an ionic bond. An ion in general is just something that's lost or gained an electron. It has a charge. One of these lost, one of these gained. They're they're now ions. They have an ionic bond. So they're all very nice. One gives, one takes. They're happy. This generally is the same thing I just drew out. There's my sodium, giving an electron over to the chlorine. They're both now happy. They both have 8 in their outer shells, and they like to hang out next to each other. What is sodium chloride? Yep, it's your salt. The other type of bond is a covalent bond. They're also very nice. And I can't draw it as well as I should, but I'll try. A covalent bond, instead of just giving an electron, and it's like, here, let me give you, and the other one's like, I'll take it, and everyone's all super nice. Instead of just giving and taking, they share. Also, still very nice. They share electrons. They share outer electrons. You can share. You don't always have to give and take. They can share. And when they share, you gain electrons. Anything you share from something else, you've now gained. Now, my example, if I had to draw carbon, here's my carbon. And if I had to draw it, because I'm going to draw it up there, but I'm going to do a little reviewing. How many protons are in carbon? 6. How many neutrons? 6. How many electrons? 6. How many go in the outer shell, or the first shell? 2 electrons. How many more do I still have to draw? 4. Is it happy with 4 in its outer valence shell? Nope. Now, because it has 4, easier to gain or easier to lose 4? This is my trick question. Either way, it's one of the properties that makes carbon so flexible. Not only can it share, it has 4 electrons. It can either give or it can take. It becomes very reactive with things. We are carbon-based. Now, is there a better example than hydrogen? I don't want to have to draw out 4 hydrogens. Nope. Hydrogen on a periodic table. Hydrogen. Say, it's like 1 and 1. It has 1 proton, 1 electron. I'm not going to get into any more details on that. But it has 1 electron in its outer shell. Here's hydrogen. There's my 1 electron. Is it happy? Nope. How many does it want in that first shell? 2. And so it's like, well, carbon doesn't want to give away all of its electrons. And hydrogen's like, I only have 1. What it can do is it can share. And so I'm going to try to draw. They share their electrons in their outer shell. So this hydrogen's like, well, I'll bring 1 to the table. Here's the hydrogen electron. And it shares. Hydrogen's like, hey, you want to share 1 with me? I'll share 1 with you. And this hydrogen's like, same thing. I'll share 1 that I have, and you can share 1 with me. Now, when it shares the hydrogen, how many does it now have in its outer shell? 2. Is it happy? Yes. And I'm like, and how many are now in the outer shell of this carbon? 8. Is that happy? Yes. And I'm like, and a lot of times, like, you see this. It's CH4. It's methane. Mm-hmm. Oh, it was protons. And I'm like, I just wasn't going to go into the details. I started a thought and I didn't finish it. So they just share. So nothing's giving an electron. Nothing's losing an electron. We're not changing charges. We're not taking anything ions. They're just sharing. They're oh so happy. This also happens in oxygen. They can actually share 2. And so all 4 of these can be counted in this outer shell, and all 4 of these can be counted in this outer shell. And I'm like, when you share 2 electrons, we consider that a double bond. It's stronger. It's not just like, well, I'll share 1 with you. Like, I trust you enough to share 2. And we draw that anytime you see something with 2 lines between 2 molecules, that means they're sharing 2 electrons. It's a strong bond. Some, even rarer, can share 3. Now, a hydrogen bond, I have a picture, good. A hydrogen bond is an attractive force between an electropositive hydrogen, that's where I get the hydrogen bond, an electropositive hydrogen of 1 molecule, and an electronegative atom of another molecule. Now, hydrogen, it does have 1 electron in its outer shell, and occasionally it will give it away. Now, because it only has 1 in its outer shell, it's an electron, it doesn't want to completely give it away, because then it leaves it with nothing. So sometimes it's kind of like, I'll kind of sneak it to you, but I'm not going to give it to you fully. And so we'll call that like a partial positive. It's not a full positive, because it didn't completely give away its electron. It's just kind of like, I'll kind of let you see it. You know, I'm like, I'm not going to give it to you, but you can kind of hang out with it a little bit. this happens, but even though a hydrogen's like, I'll kind of let you see my extra electron, and someone else is like, fine, I'll take that, they form a weak bond. So it's not a very strong bond. An example of this is water. Now, H2O, these weird little squiggly S things means partial. So it's not a full positive, it's not a full negative. And so anywhere there's a hydrogen, and on water, when you draw out the water molecule, they kind of look like little Mickey Mouse heads. The hydrogens like to hang out on one side of the oxygen. And I'm like, so both hydrogens are hanging out together on this side of the oxygen. So where the hydrogens are, a little more positive. And on the other side of the oxygen, it's a little more of a negative charge. If you put enough water molecules together, the negative side of the oxygen is slightly attracted to that positive side of the hydrogens. And they form these hydrogen bonds between water molecules. Water likes to stick to water. It's not a strong bond, but water likes to stick to water just because of that partial positive of the hydrogen and that partial negative of the oxygen. Now, why this becomes important, and I'm like, well, for lots of things. I don't think we get to our water part. But water does a lot of things, and it's good that it sticks together. Because it sticks together, it has that partial attractiveness between positive and negative. Water likes to stick to water. And yes, you've seen these bugs before in the summer. And I'm like, when bugs can look like they're walking on water, they can do that. They do not weigh enough that they don't break the bonds. That partial positive, partial negative, those hydrogen bonds stay intact. Now, can you walk on water? No. Let me know if you can. But no, you cannot walk on water. When you try to step on water, every time you would step right in the water, you are breaking every single hydrogen bond that's there. These guys are light enough, they don't break those hydrogen bonds. Now, on to review. So, last time, pull out your colored note cards. I have colored note cards for you, Sam. Pink, orange, yellow, and green. Did anyone forget their colored note cards? Now, pink, orange, yellow, or green. Which of the following is not an example of matter? Did you forget yours? I brought it. I always bring it. Is green. Now, I tried to make it because what three states can matter be in? Solid, liquid, and gas. So I put up there a solid, liquid, and gas. Energy is not a solid, liquid, or gas. It can move some of these other things. Chemical energy is what? Fill in the blank. It is the green. It is both orange and yellow. Chemical energy is stored in bonds, and because it's stored, it's also a type of potential energy. Now, the 4 elements that comprise about 96% of living matter are and also a theme with my colors. I need to rearrange these. It is still green. I don't know why I have all these green. I just switched around the two. But yes, it can spell CHON, carbon, hydrogen, nitrogen, and oxygen, or carbon, hydrogen, oxygen, nitrogen. I didn't ask in order. What is contained in an atom's nucleus? Yeah, eventually I do start switching colors. It is the protons and neutrons are both found in the nucleus. The most important determinant of an atom's bonding behavior is what? What determines if it will bond or not? It is the yellow, the number of valence electrons. I'm like, so it's the which, how many are in the outer shell? Is it 1? Is it 8? When atoms gain an electron, what happens? It is green again. They become negatively charged because electrons are negative. Covalent bonds occur when? It is the pink for everyone that's pink. Electrons are shared. That's the big one with covalent. They share their electrons. They're not giving, they're not taking, they're just sharing. I was going to say, yes. I'm trying to remember, what was I just erasing? Yep. That was the covalent example. They were sharing between the carbon and the hydrogen. Hydrogen bonds are similar to ionic bonds because what? It's pink. Both are due to opposite charge attractions, whether it's partial positive to partial negative. One gave an electron, one took, one became positive, one became negative. They liked each other. Let me